So I'll be giving you an overview of some work we have been doing recently at Argonne. So I'm a staff scientist in the Maths and Computer Science division, and we are really interested in using machine learning, in particular deep learning, more modern methods of deep learning for learning dynamical systems. So, so let's get started. Oh, if my clicker works. Yeah. So let's talk a little bit about the motivation of some of the work that we're doing. I know there are a few people in the audience who are coming from the dynamical systems community, and I know at least one person who is coming from the dynamical systems modeling community as it relates to weather and climate. But these two pictures over here show a couple of, I guess, inspiring is the right word, simulations that have happened in the last year or so related to the weather and climate modeling community. On the left is a simulation that was run at Argonne using E3SM, which is a US Department of Energy flagship code for climate modeling. And for the first time in many decades, climate models such as E3SM are starting to resolve clouds, which traditionally all the projections we've got for example, climate change have been done by have been obtained by by modeling clouds rather than resolving them. So we are at a tipping point when it comes to how predictive our models are going to get. And of course, as you can see, these are simulations that are run across multiple months, and they are generating multiple almost mind-boggling amounts of data. So for example, the simulation on the right is a weather simulation that actually made the plenary of supercomputing in 2020. It's a simulation run by folks in the European Weather Forecasting Center, ECMWF, and you can see that the forecast is actually also, if my clicker works again, validated by satellite observations. But on the right you have a weather model, on the left you have a climate model. So we are now, as computational scientists, I'm a computational scientist, I'm not a weather or a climate scientist, at a position where geophysical scientists or geoscientists are asking us to do something with this data. Okay, we are generating huge amounts of data. We don't just want to visualize it and make videos. We actually want to, you to assist us in your computational workflow. So by training, I have a PhD in aerospace engineering, and at least in the mechanical and aerospace engineering domain, we've had several years of success in doing what we call surrogate modeling, right? It has different terms in different domains. So some people call it emulation, some people call it surrogate modeling, some people call it parameterizations. What surrogate modeling does is basically build alternate pipelines to quantity of interest prediction using data. Okay, so for example, if you are to look at the red pipeline over here up top, where you have some design parameters, you generate data for these design parameters using simulations. If you're lucky, these simulations have already been performed and stored in a repository somewhere online, which again the climate community and the weather community does really well. And then you get some outputs from these, right? These could be the state itself, but more generally speaking, these could be quantities of interest. Our goal is to then use this data that's available or generated and build an approximation for this usually costly pipeline, the simulation, using a data-driven alternative, which is fast to evaluate. It's cheap, right? And if we are successful in doing that, modulo some where success is defined modulo some issues related to the issues related to machine learning in general, which we'll speak about today, we can run compute-intensive tasks such as control, optimization, sensitivity analysis, which require several forward evaluations, right? Forward evaluations are not desirable when you use simulations because they are costly, but they are desirable when you use surrogate models because they are cheap. Okay. All right. So in this particular talk, we'll be looking at emulating or surrogating dynamical systems from data. But we'll also add a little bit of an extra constraint. Our constraint will be that we do not know anything about the dynamics of the data. We just have observations. Okay? So if you are to go back to a surrogate model or reduced order model paper at the turn of the century, like early 2000s, or if you go back to the late or mid 90s, you'd see that there was a huge focus in developing surrogate models by using the equations that you already had. So let's say you have Navier-Stokes, let's say you have Maxwell's equations. You try to build coordinate transformations for your equations so that the computation of these equations would be cheaper, right? But you'd still have an equation at the end of the day that gives you a quantity of interest at the end. Now, for certain domains, and weather and climate science is one of such domains, you, in some sense, are limited at the onset of your computational science because the equations that you have are themselves not very precise. Okay. For example, if you are doing weather forecasts, it's common practice. It's actually established practice. The forecast from your model is assumed to go wrong very quickly anyway. And then what you do at that particular time is you have observations coming from weather stations, from ships, from drones that go in and correct your model anyway. So in some sense, we have broadband. We have that budget for making a bad prediction because there are established approaches to actually fixing them. Okay. So that's why we want to build models where there are no closed form governing laws. Okay. Okay, and so this is this is joint work with several collaborators both at Argonne and at other labs and universities. So I just want to acknowledge them. Okay, so let's look at some of the technologies we'll be using today from the machine learning perspective. So this slide is a brief overview of what is called the neural ordinary differential equation. I don't know why people call it an architecture. It's for someone who's been studying dynamics in the past, it's fairly natural to have an equation such as one where you make an assumption that a state A evolves in time, but the right hand side of that state is unknown. So you learn so-called the right hand side using a neural network. So you've looked at neural networks yesterday and today. This particular approach where the right hand side is trained using stochastic gradient descent actually was awarded the best paper award in I think NeurIPS 2018. It was very surprising to a lot of people in the dynamical systems community because this general idea has been around since the late 60s. Of course, we didn't have GPUs in the late 60s. We didn't have ATPESC in the late 60s either. But now this, it must be acknowledged that a lot of strategies that have been around in computational science since the 80s and 70s and 60s are becoming attractive again because of access to hardware now. So we revisit them and we get certain rather impressive results, as you'll see. Okay, so going back to this architecture, the idea, as you said, is have a neural network given by parameters theta that learns how to update the state in time. Okay. Now, what is interesting about this particular architecture is that instead of evaluating a discrete version of equation 1 and calculating the loss and then using that loss to change theta, the parameters, they formulated a continuous analog of backpropagation by solving the adjoint. So you can actually look at this equation, and f over here is a neural network which is differentiable, as you know, right? You can write a loss function which basically measures how trajectories diverge. So let's say I pick a bad value of theta initially. That's how I initialize my neural networks. Let's say I have examples of a in time. I can evolve my system, get a garbage answer initially, but that garbage answer then is sent to my optimizer to improve theta. It's just that the process of optimization requires a backward solve of this particular ODE in equation 4. Trust the algebra on this, at least for the purpose of this talk. But what the benefit you get for this is that you don't have to save intermediate steps. So when you go from a at t equal to 0 all the way at a at t equal to capital T, you have to save steps in the middle if you were to calculate the loss of your trajectory, but the adjoint formulation lets you save on that memory. So that was the novelty of this method. Okay. All right. So the best way to learn is to dive into an example. So let's start with an example. Okay. So the first example that I personally like to look at is given by the Kuramoto-Sivashinsky equation. So this is a one-dimensional PDE. I talked a lot about climate and weather, and I'm giving you a one-dimensional PDE. I hope you're not upset. I will have an example that has something a little more realistic. So this particular configuration, 5 and 6, causes a very interesting behavior in the system. It causes a chaotic behavior. Okay, so a chaotic behavior with a steady state attractor. What does that mean? It means that if I start if I simulate the system with two initial conditions, which are just infinitesimally different from each other, they will follow a trajectory that's similar for a short amount of time and then diverge. but this divergence is not an artifact. It's how the physics behaves. So this is the physics of deterministic chaos. So it diverges over time, but in the steady state, you have a statistic that emerges from this system, which is the chaotic steady state, and this statistic is a reflection of the physics. So this is the worst possible problem for a machine learning forecasting algorithm. How do you train a machine learning forecast algorithm? I'm asking a question. How do you train a machine learning forecasting algorithm? How do you train any machine learning algorithm? You use the data. What do you use? You use a metric, like a mean squared error, right, for example. It's the worst possible metric for this case, because in the short term, maybe mean squared error makes sense, but in the long term, the system itself, the physics is supposed to give you a high mean squared error, even though it's perfectly accurate, right? So if you take solutions from the system and put it into an LSTM, a transformer, whatever they're selling you nowadays online, it will not work, right? And that's kind of what motivated us to look at it. So over here, after quite a few months of thinking about it, we realized that we have to go back to the basics in what we know about chaotic systems to actually introduce a new type of architecture that can capture chaotic dynamics. Okay? So on the right over here is what I just told you. So you have the evolution of a state as a function of a neural network on the right-hand side. On the left is what we proposed, a modification to the neural OD that exists out there, where instead of having solely a nonlinear term, we have a linear term and a nonlinear term in an additive manner. Okay? Where the linear term over here, and why we use a linear term will become clear soon, is designed to be linear by our understanding of, for example, the grid, the dynamics, and the boundary conditions. So over here, how would you write down a linear term in a finite difference method? You do +1 -1 divided by whatever the stencil width is. We do the same thing over here, except that we let the optimization discover the linear term for us, right? So if we prescribe the fact that there are boundary conditions, the diagonal is the green number, the green box, the -1 element is pink and the +1 element is yellow, and we constrain them appropriately, we will design this operator to be linear, come what may, whatever the optimization tells us. Okay, and then everything else is the same. We still train it using the adjoint method, and so on. Okay, so let's look at how this actually works. So up top, you have the first row is our test data. So we solve this Kuramoto-Sivashinsky equation system by sampling random initial conditions on an attractor, so on a pre-solved system. And if we evolve it for a short duration, you get what you get in the first column. And if you evolve it for a sufficiently long duration, in the last 50 time units, you're seeing behavior on the attractor. Okay? The second row is what you get from a regular neural OD. So the regular neural OD that you can pick up from the paper that was published in 2018. You see in the short term, you get behavior. I have more quantitative results shortly, but in the short term, you have behavior that across all these methods I'm showing you is relatively similar, right? This is what you'd expect from a standard machine learning algorithm because it penalizes mean squared error. So in the short term, you get the required accuracy that you desire. But look at what happens in the long term. The neural OD has no understanding of the fact that this has a chaotic sort of steady state behavior. So it comes up short in the sense that it may generally blow up. That's what we observe. And in the odd event that it actually converges, you get these non-physical sort of high wave number striations. Okay. Now the bottom two rows over here are deployments where we actually built in the linear term into the right-hand side of the neural network. The third row is one where we cheated. So in this case, we know the Kuramoto-Sivashinsky equation has a particular linear term. It's given by, like a negative Laplacian and a negative of a fourth order term. So we built it into this manually, right? So of course we got a decent result there. But when we actually learned the linear term using the optimizer itself, we're able to retain a similar type of behavior. Okay. So in more quantitatively speaking, if I am to look at the mean squared error, again that metric which we claim is not as good for this particular problem, in the short term, ensemble results for the mean squared error across multiple initial conditions, you see that there's not much difference between the different methods, right? This is what you'd get from any numerical scheme for the KS equations. You'd have zero error initially because they all start at the same initial condition, and then over time the error grows and then it eventually saturates because that's when deterministic chaos has set in. trajectories have diverged completely. Okay? But on the right, that's when things get interesting. So what I'm plotting over here is a joint PDF of the second derivative of the state and the first derivative of the state after it has reached the chaotic attractor. And you get this, this type of teardrop type shape density that's a hallmark of this chaotic steady state. And you see that the true data and the data generated by this novel, augmented, stabilized, whatever you want to call it, neural OD, match closely, but the regular neural OD, even if it has converged, you end up getting spider webs basically. So it's basically not able to capture the behavior of this system in the steady state. Okay. Now, there are some advantages over here. How much time do I have? Okay. So the advantages over here are once we've actually learned the linear term, right, we can go back to numerical analysis, and there is a rich body of literature in actually what is known as approximate inertial manifold theory, where the linear term in a particular PDE can be used to do a lot of cool things in your system. So for example, you can take a eigendecomposition of the linear term, right, and you can look at the eigenvalue spectrum of the linear term, and the eigenvalue spectrum of the linear term tells you a lot about the dynamics of the system. For example, if you have something called a spectral gap condition, right, which means that there are some eigenvalues that are orders of magnitude greater than the others, it means that there is an underlying attractor in your system. Okay? So when we actually went in and checked the eigendecomposition of the A matrix that we learned, we saw that it was replicating the eigenvalue decomposition of the original A matrix, which is given by the PDE, very well. The linear term we were learning was not precisely the same as the linear term in the original PDE, but the eigendecomposition was matching, right? Okay, so let's say you take the eigendecomposition and you find what the eigenvectors are. You can retain a few of the eigenvectors and identify a coordinate transformation for your system, which actually reduces the order of your surrogate model. So that's why I call it flipping the script over here. So when you're building a reduced order model of your system, you generally look at the data, compress the data, right? You compress the data, then you build a forward model of your compressed data set. Over here, we build a surrogate model of our high dimensional data set, and then we use an eigendecomposition of an element in our neural network to obtain a reduced order model. So what do we do? So once we find this projection matrix, you can generate a set of resolved and unresolved variables, 7 and 8, just by applying the capital P matrix on the PDE and the complement of the capital P matrix on the PDE. So the complement of the capital P matrix is I minus P. Okay? And once we do that, we can only solve equation 7 and ignore equation 8. Right? Equation 8 is the so-called unresolved or unimportant portion of our dynamics. One way to ignore this is to literally just ignore it, put q equal to 0, and just solve for 7 with q equal to 0. The other way is to assume that dq by dt is equal to 0 and solve one linear system, one iteration of a linear system. So you get q equals A inverse qp, put it back into 7 and solve equation 7. Okay? When we do this, you'll see again that we are looking at the statistic in the steady state. That's our quantity of interest. What I'm plotting here on the y-axis is the KL divergence. So this is the distance between the predicted statistics and the true statistics. It's a distance in statistical space or density space. And the y-axis is the dimensionality of the reduced system. So our initial system was on a grid of dimensionality 64. Our reduced system is on a grid of dimensionality p, where p is given by equation 7. And to get equation 7, you have to decide how many eigenvectors you keep in your eigendecomposition. Okay? So when you look at the Rn squares, these are results coming from when I solve equation 7 by just putting q equal to 0. And when I use the correction of q equal to A inverse capital QP, which is the approximate inertial manifold, you get the blue circles over here, which are obviously more accurate because you've accounted for the stationarity of the unresolved scales. Okay? The green crosses over here are basically the process of post-processing. It was a paper introduced in 1993, where you can solve for our system, for the Kuramoto-Sivashinsky system, initially using the Galerkin approach and do a post-processing approximate inertial manifold correction after the fact. Okay. So let's look at another example very quickly. So this is a system which is given by the Burgers equations, again one-dimensional, with a very, very low viscosity, a to the 10 to the negative 4. So you're expected to get shocks in your system, right? This is another type of case when neural networks have a lot of trouble. Again, the results are similar. So over here we compare across the true data for different superpositions of sines and cosines in the physical space. We compare against the fixed linear approach, which again, like I said, we exactly specify what the linear term is, and the CNN, we call it a CNN because we subclass the CNN module to build a learnable linear term. So what you get over here is that when you use a regular neural ODE, you'll get all these oscillations which are non-physical, similar to the non-physical oscillations we got in the KS equations. But when we use the linear term, which in our opinion is acting like a regularization over here, you're able to stay smooth and actually capture, in many cases, the location of the shock quite nicely. Again, for quantitative assessments, what we are plotting here is the mean squared error between the truth and the prediction. The neural ODE, of course, it blows up in terms of relative error quite quickly in 5 time units, but the linear term keeps this bounded because it's able to learn the right damping of these oscillations. Burgers is often used for turbulence prototyping, turbulence model prototyping. So over here, when we do a power density spectra analysis in the wave number space, you're supposed to get a k to the negative 2 scaling because of the presence of these shocks at a sufficiently low viscosity. As you can see for the neural ODE, you remember I made a hypothesis that we were getting high wave number oscillations from the neural ODE as we evolved it in time. You're able to see the same thing over here. The orange line is evidence that the noise basically accumulates and is not dissipated, as that the right model, the right physical model should do. So in comparison, you'll see that the linear augmented neural ODEs are able to, even when you learn the linear term, are able to, of course, respect the scaling in the inertial range, but also dissipate adequately. This is a plot where we add noise to the initial condition. When we add noise to the initial condition, again, the neural ODEs, the regular neural ODE is even worse, so it's less robust to noise. In comparison, the linear term, again, it's a regularization in this case, so it's more robust to noise. Okay, more results on the same. This is an interesting experiment where we actually we learn a neural ODE, or we learn the dynamics not on the original grid. So of course, you can for certain problems, you can observe the solution on the same grid that it's generated because the observation instrument that you have is able to resolve all the scales in the physics, but that is more often than not the case. So over here, let's say our original dynamics needed 4096 degrees of freedom to resolve, right? Because there are these very fine shocks that are present, but we observe only 64 degrees of freedom, so spaced out quite coarsely. As you can see, when we learn the dynamics on this coarse grid using the neural network approach that we introduced, we are able to actually stabilize the evolution of the dynamics quite nicely. So this is evidence that not only are we learning the dynamics, we are also learning its closure on a coarse grid for this particular case, right? Whereas if you were to just solve Burgers' equation on 64 degrees of freedom, you'd get these blue dots, which is all over the place. So 64 degrees of freedom is not sufficiently resolved for a native simulation of Burgers. How much time do I have? Okay, I have 3 minutes. Let me accelerate. Okay, so I promised you something that is a little more real world and practical. So this is a data set that is that, of course, here at Argonne we have studied quite a bit. So this is a sea surface temperature data set that's collected through ship and satellite observations and hosted publicly by NOAA and is actually quite popular with numerical analysts for prototyping some of their equations. So the coarse data set is actually quite, so the data set available online is actually quite fine. It's on a 0.25 degree by 0.25 degree grid, but we subsample it to have it on a 1 degree grid. So 1 degree grid data set is basically a 180 by 360 image. So it's 180 degrees for longitude, 180 for latitude, 360 for longitude. And of course, we do our training and testing split like we did for all of these guys. So 6 years for training this neural ODE to capture the dynamics of this particular problem, and testing it for 30 years. Okay, so let's say we wish to learn the evolution of this system. Instead of applying it on the native grid, which was 180 by 360, we actually did a coordinate transformation using POD, so proper orthogonal decomposition. This reduces our system from 180 by 360, where you have some computational trouble in specifying what this linear term is, right? So the linear term requires a stencil computation, which will now be 2D. And then one of my biggest pet peeves about climate data sets is the fact that it's not actually a square or a rectangle, right? It's actually on a geodesic. So how do you compute derivatives at the upper boundary of this not square, right? There's a singularity over there, technically speaking. So I try to avoid using finite difference schemes on at least the non-geodesic projections of these types of data sets. So we use POD to do a coordinate transformation, where the linear term application is a little more mathematically sensible. So on the left, when we apply a regular neural OD, you see that it finds a spurious fixed point. Okay, so this is a common failure mode in long-term forecasting of dynamical systems from data. It'll either blow up, right, which we saw in some previous examples, or it'll find a fixed point. It'll detect a stable dynamical system, which is not sort of the invariant behavior that we expect from the system, which is the Earth's climate. The Earth's climate has somewhat of an invariant behavior because the seasons come and go as you'd expect them to. So on the right, you have the behavior from the novel proposed neural OD, which is the orange dotted lines over here. And you can see, even though it misses the amplitude at a few locations, it's able to capture the frequency of the seasons quite nicely. Okay, if we are to go and probe these the dynamics a little closely, okay, there's a lot of information on this slide, but I want you to focus on the fact that these blue lines over here, which have these small oscillations, that's the prediction from the regular neural OD. As you can see, it's not able to capture. It's just revising what I said in the previous slide. It's not able to capture the right amplitude and the frequency of how the temperature is supposed to behave at one point in the ocean, not just in the sense of the global magnitude. I have comparisons over here for the different our approach in the yellow lines, and a couple of models over here which are in some sense, it's not really a fair comparison. It's not really an apples to apples comparison. Yes, question?
What are the axes on this?
Oh, sorry, it's poor plotting on my part, but the axis is weak, and the x-axis is Celsius. Sorry, yeah. So it's temperature against time. So the red model is something called CSM. CSM is a climate model that's like a once in a decade type simulation run using ridiculously large amounts of high performance computing. HiCom is a weather model that's run by the US Department of Defense every 48 hours. So it's a smaller compute, but maybe it adds up if you have to run it every day. So I have more quantitative metrics in a while. This was just to show you how the stabilized neural OD does better than what is already out there. Okay, over here, over 8 weeks, I'm actually plotting what the root mean squared error is for different so-called models. So right at the bottom, you have something called HiCom, which is the weather model, which is most accurate. This is not a surprising result. Weather models are more accurate in the short term. It's just that weather models don't give you 8-week forecasts. They just give you like 2 or 3 day forecasts before you have to reinitialize them. So that's why I said it's not really a fair comparison. But I can chain together weather forecasts in the 90s and make this plot for you. But basically, the right plot to make would have been 0, 1, and not applicable all the way till the 7 for this red line over here, right? This is our performance, which is of course worse than the weather model in the short term, but in the long run, you get a forecast, which the weather model does not give you. The orange line over here is the regular neural OD, which is worse. We've gone through that. The purple line is climatology. So what is climatology? Climatology is basically an almanac prediction, how people used to make weather predictions in the, late 1800s, which is, it rained last year around this time, so you know what, we're going to assume it's going to rain again today, right? No computation involved, just going to the public library and looking up what the weather was like in the past. And over here you have CSM. Again, not an apples to apples comparison because CSM was run on a slightly different grid. Even HICOM was run on a slightly different grid. So this type of error is somewhat assumed. Also, CSM is run for a 2-century time period. It's not run for, again, for like a 30-year time period like we ran it for. So, so it's a little difficult to compare, but again, people like to have these anyway. So, okay. So, finally, the most important thing, was it worth it, right? So, in order to construct our, what I've been trying to sell you, this neural ODE thing, it was 2 node hours of a CPU-only laptop. I don't actually know if it was 2 node hours. It was just 2 hours from me sending this to my grad student intern and them getting back to me. So it could be much less, but that's what I assume it is. Again, HICOM, these are numbers I picked up from their website. So they require 44,800 core hours per forecast day. This is, and they have to run a forecast every day. CSM, like I said, is a once-in-a-decade type computation, which generates data for policymakers, for scientists, for consumption for many, many years in the future. So that was obviously not comparable. That's a 5-10 million core hour type of cost. So, and so with that, I'd just like to say that this emulator business that I'm trying to talk to you about, it's definitely not meant to be a replacement for CSM or HICOM. It's common to have these types of statements in literature nowadays, which are like, oh, ML is going to solve all your problems. Everybody else can go sit at home, find another career. No, it's not true. This is meant to augment the workflow, the computational workflow that you have, which is definitely something my community has always invested in. If you're having some sort of data assimilation task or control task or sensitivity analyses, these emulators can be your friend in that they will dramatically reduce the cost of your computational workflow. Okay, so we're actually talking to a few people in the EVS division to see if these sorts of emulators of slow-moving variables can actually act as boundary conditions to a model where there are other variables that you perhaps don't trust database models to predict so well. So you can have like a workflow that has a significantly reduced computational cost overall, but still preserves the required level of scientific accuracy. Okay, with that, I'd like to stop. Thank you. Some references. Thank you for your attention, and I'll take any questions. Thanks.
Are you familiar with the dynamic mode decomposition?
Yes, I'm familiar with it.
So how does your linear operator compare with the DMD operator?
So,
The learned one.
so I haven't made a comparison directly, but people have tried to use DMD for the SST, and but they have not used it as a forecast tool. So they've used it mainly as a post-processing tool where they want to see how the DMD modes, the eigenmodes, correspond to trends in the sea surface temperature. So for example, they wanted to discover that there is a oscillation that's happening around the Pacific, the El Nino oscillation, so the DMD eigenmodes were able to detect that. In my personal experience, for data sets that have shocks and that have advecting nonlinearities and things like that, DMD does not work because it's trying to linearize the system. If the system is inherently nonlinear.
Sorry, so just for your the linear mode that your model is able to reconstruct,
Okay.
that should be equivalent to the DMD modes, right?
I haven't made a comparison, but why?
Because the DMD modes are the linearized dynamics.
DMD modes are the linearized dynamics, yes, but the modes that I'm extracting are not linearizing the dynamics though.
No, the A operator that you
Sure.
is supposed to be linear dynamics.
I haven't said that. No, I'm not. So in our case, our A operator is kind of like a regularization operator. It's not doing linear dynamic. It's not linearizing about anything. Does that make sense? So you have a nonlinear term and you have a linear term, right? I'm not there. The nonlinear term may also have some linear effect, right? We are not explicitly separating the two. Okay. Mm-hmm. Yes. Question.
Okay. I was very happy to see that your model beats climatology, which not all models do. How did you calculate that climatological figure?
So we had training data from 1981 to 1987. So we computed, so for 6 years, we have predictions at a particular day. So we took the average of the 6 predictions, and that was the climatology forecast. Yeah, is that about right?
It makes sense.
Okay.
Yeah, I was a little concerned that maybe you weren't accounting for the rolling average because sea surface temperature is increasing over time.
Okay, no, we didn't account for that. Okay.
I guess if I understood you correctly, so basically you're decomposing the time evolution terms. I mean, basically, you're decomposing the time evolution into two terms. One is a more regular term, which is linear in time, and the other way maybe just essentially chaotic.
The residual effects. Yes.
So, but the first term is not necessarily going to be linear.
No, not necessarily.
Okay. So in other situations, for example, we have more complicated dependence on time of the regular term, and then there's another chaotic term imposed on that.
So the only decomposition we've done is linear plus nonlinear, where the linear term is fixed over time. So now we did explore making the linear term a function of time itself, so a function of the state, but that introduces problems in the training. It makes the system difficult to train. So we kept it simple. So the A term is fixed during training, and then in the sense that once we have trained it, we don't change it over time. And then you have a nonlinear term which acts as the residual sort of for the linear dynamics. So it's kind of like,
If you could, for example, design a term which is stable, then we could make other differences.
Yeah. So you could explicitly design stability by specifying what A is, right? You could just put the numbers in A, and then yes, you could learn a residual to that as well.
And in principle, this can be applied to, for example, stock market.
I'm sorry, it could be applied to?
Stock market.
So, I don't want people to lose money because of me, so I'll leave it at that. Yeah. Any other questions? Yes.
You applied it to viscous Burgers equation. Do you plan to apply it to Navier-Stokes? Have you applied it to Navier-Stokes?
Have I applied it to Navier-Stokes? Not yet. So there have been some people who've applied the regular neural OD to Navier-Stokes. You may have seen those. Of course, things that get published are usually the success cases. So we'll have to see. We were thinking of KS, Burgers, Navier-Stokes, but we decided directly to go to sea surface temperature to see how it works on a case that makes more practical sense, right? So, good question. Okay, then I will stop there. Thank you.